During the long, bitter struggle of the Second World War, one weapon was paramount to the final outcome of victory. A weapon that was so secret it was almost never spoken of. On land, air, and sea, it was a weapon that spanned the globe. It brought together the world's top scientific and military minds. It brought women for the first time into the front line of battle. It also helped deliver the most destructive force of World War II. Yet this was a weapon that was invisible to the enemy. It was called radar.
Every single battle that was fought by Americans, by British troops, radar became a key component.
We saw it grow up, and it became our tool to help defeat the enemy. Thank God for radar, United States Navy.
Using extraordinary archive film and color reenactments, Battle Stations uncovers the invisible world of radar wars. At a secret meeting in Berlin on February 26, 1935, Adolf Hitler officially created the German Luftwaffe. Appointing Hermann Goering as its commander-in-chief, they were creating an air force that intended to destroy everything that stood in its path. Little did Hitler and the top Nazi chiefs gathered for this momentous occasion know that on that very day, a small van was making its way to a remote meadow near the English village of Daventry. Inside was a 43-year-old research scientist named Robert Watson Watt and his assistant, Arnold Watkins. What they were going to try and prove was that it was possible to detect an aircraft before it saw you. Until that time, the only way of obtaining advance warning against attacks by aircraft was either by spotters on the ground or from fighters hoping to locate them in the air. As German bombers became faster, such methods were not enough to prevent an attack. Something else had to be found. Since the early 1930s, scientists in several countries had been experimenting with radio beams. It was known that when these beams hit certain objects, they were deflected. Yet, was there a use that this knowledge could be put to?
Well, of all these places in the world that invented radar, Britain was the one that had the most pressing need to fast forward its development as a defensive weapon. They knew that you had aircraft that were going to be capable of delivering bombs, and this previously isolated island was an island no more.
In 1934, the British Air Ministry set up a committee under a prestigious Oxford-trained chemist called Henry Tizard. His task was to investigate new technologies as an effective defense against air attacks.
They looked at things like infrared detection, acoustic mirrors, acoustic warning systems, barrage balloons, and even this idea of a death ray that somehow could find enemy pilots and zap them in the cockpit.
The Air Ministry offered a prize of £1,000 to anyone who could build a death ray that could kill a sheep at 100 yards. Although this appeared to be in the realm of science fiction, at the time the British government was worried that the Germans were working on such devices.
Robert Watson Watt was asked to investigate this possibility. When he examined the state of science and technology, he realized quickly that a death ray was not feasible. But he proposed this alternative idea, and this was the idea of radio detection.
The Tizard Committee were enthusiastic, but before they committed the necessary funds to develop this theory, they needed a successful demonstration. Watson Watt had known that when an aircraft flew over a radio transmitter mast, it caused a fading of the radio signal. After a series of trials and experiments, he was ready to prove his theory. He asked an RAF Hayford bomber to fly a course between two BBC radio towers. Inside the darkened van, they intently watched the screen for some sign of the aircraft. Slowly, they saw a faint but unmistakable blip magically appear. As the plane moved from left to right, so the signal changed in length. As the aircraft flew at different heights, again the signal changed. The blip remained on the screen until the plane was 8 miles away. The experiment was totally successful. It was a revelation. Watson Watt apparently exclaimed, "Britain is once again an island."
He foresaw, even then, the possibility that Britain could erect what was essentially an electromagnetic burglar alarm all around its shores that could see out tens, if not 100 miles to detect German bombers on their way.
Robert Watson Watt's system went into overdrive when in 1936 the British government saw the havoc that Hitler's Luftwaffe had inflicted on cities and the civilian population during the Spanish Civil War. It suddenly became clear that waves of enemy bombers could fly over their cities, leveling them in a rain of bombs with absolutely nothing to warn of their approach. Soon, 350-foot-high radar towers began to sprout up around the coastline of Britain. This was the beginning of a construction program that would enable the RAF to search the skies for any threatening sign. The towers, however, were not always greeted with enthusiasm. Local landowners were worried that they might actually interfere with their hunting. By late 1938, Britain had constructed a series of these towers all along the coast of Britain. From Portsmouth in the south to Scotland in the north, each tower's transmission range extended to over 100 miles. Together, they formed an invisible shield that no aircraft could penetrate undetected. This entire web of surveillance became known as the Chain Home System. By mid-1939, reports from German spies in Britain were reaching the Luftwaffe that a number of tall masts had been erected along British coastal sites. To the Germans, this indicated that they must be associated with some form of military radio or radar. It was crucial to the Luftwaffe to try and discover what the British actually had. To this end, the Germans decided to use an obsolete method to find out the true state of British radar. They commissioned the retired Graf Zeppelin airship. During the summer months of 1939, this grand old lady of flight was flown up and down the British coastline. This was to become the world's first electronic surveillance mission.
Now, one day, it was the 3rd of August, 1939, the CH station observed a massive echo approaching from the east at about 60 knots. Far bigger echo than they'd ever seen before. And their first reaction was that it was an invasion fleet with barrage balloons to protect it from an air attack. We tracked it on radar the whole way.
The Zeppelin was crammed with electrical surveillance equipment. But as the Germans flew over the masts, all they received was meaningless clutter and static. Mistakenly, the German team was monitoring the wrong frequency, or wavebands. It would be one of the costliest mistakes of World War II.
Now, we concluded that they had been accurately observing our radar system, so they would have gone back loaded with that information. We assumed that as soon as war broke out, we could expect a massive attack on the radar system.
For the confused Germans, all that their equipment told them was that the British had no operational radar. They thought the towers might have been some form of civilian aircraft landing system. Hitler and Goering were delighted. They now felt that when the war came, the Battle of Britain was as good as won.
Goering was entirely dismissive of what he called these radio installations. You don't fight a war with radio installations, you fight them with bombers.
By the outbreak of World War II on September the 3rd, 1939, the whole of the vulnerable east coast of Britain was now under continuous radar watch. Robert Watson Watt's system had been improved to the point where it could detect an enemy aircraft by day or night in any weather. It had taken only 4 years to reach this point since that first experiment in an English meadow. Yet the period of development was now over. The first bombers were about to wreak havoc on Britain. Radar was about to be put to the test. With the outbreak of World War II, the world held its breath as Hitler's army swept over Europe. Only the narrow English Channel now stood between Britain and total defeat. Hitler's plan to invade England depended on his Luftwaffe taking control of the skies. Hermann Goering boasted that his Luftwaffe would smash the RAF's fighters within a month. An integral part of Britain's defense plan against such an attack was Robert Watson Watt's chain home system. But with nearly every man in Britain involved in essential war work, a way of manning these radar stations had to be found. The solution was simple. They were to be staffed almost exclusively by WAAFs, the Women's Auxiliary Air Force. These women, some as young as 18, were amongst the first frontline women used in war.
I was interviewed by a WAAF officer. I'd never seen a WAAF officer in a uniform before because there were not any uniform for us. But of course, she'd bought her own. And I thought, oh, if I wear one like that, it'd be all right.
We were all volunteers, I must say. Creme de la creme, of course. We had 2 Canadian girls. There were some very, very nice girls there.
Trained in the new use of radar and plotting room procedure, these women would hold the balance of the forthcoming Battle of Britain in their hands. Speed in getting their information to Fighter Command headquarters was paramount. A fighter plane needed 13 minutes to reach its operational height. A German bomber could cross the English Channel in only 5 minutes. This meant that with the 20 minutes warning radar could give, there was almost no room for error. The fighter room commander needed exact information as to height, number, and position of where the bombers would be. He would then decide which squadrons of fighters to scramble to meet the enemy. The gathering of this vital information fell to the women in the radar and filter rooms. When a radar station spotted a contact on their screens, they telephoned this information to the filter room. Here, around a large-scale map of the British coastline, stood the WAAF filter plotters. As each radar contact was phoned in, they placed on the map colored discs to indicate the position of the contact.
One of the problems of the early radar stations, the chain home stations, is that they were not very accurate. They had the shortcoming that you got a plot on an incoming aircraft. Its observed position was not its true position. Its observed height was not its true height. So we had a process of calibration.
This was the job of the filter officers. These recently recruited scientists with knowledge of radar would assess the counters on the table and decide whether the information from other stations related to the same aircraft. If they did, they would replace the counters with a rectangular marker. An arrow was then added to show the direction of the contact. With all these officers and plotters shuffling counters round the table, it resembled a frenzied children's game and was known as Mad Ludo.
You were hit by noise and heat and bedlam. So it was very noisy, very, very hectic.
On a viewing gantry above the table, a WAAF was listening to Fighter Command headquarters. It was her job to monitor the movement of friendly aircraft from radio messages. If the plot on the table matched the track of friendly aircraft, she would illuminate the plot with the letter F for friend from a light gun. The other tracks would be marked with the letter H for hostile. Once the filter officer saw the letter H, he would immediately inform the Fighter Command room, giving them position, height, and direction of the German bombers.
Britain was vastly outnumbered in terms of planes, and it couldn't afford to keep flights aloft at all times just waiting for an attack to come. It had to husband its resources in some way, and this was the key, this integration into a command and control system that got the right planes to the right spot.
As the summer of 1940 approached, Goering was poised to unleash the might of his Luftwaffe against Britain. He had over 3,000 aircraft, Britain had just 600 fighters. But as its eyes and ears, the RAF had Watson Watt's chain-home radar system. Throughout the build-up to the Battle of Britain, Wolfgang Martini, the Luftwaffe head of signals, had become convinced that those masts dotted along Britain's coast were much more than aircraft landing towers. He finally persuaded Goering to allow the Luftwaffe to bomb them. It was Sunday, August the 8th. At 1 o'clock in the afternoon, 19-year-old Avis Parsons was alone at her radar post.
When they started to send the 100-plus over, that 100-plus aircraft had never been seen on a radar screen. And it was just, it's difficult to say, it's just a blurred mass. And we had to almost guess how many aircraft there were. Suddenly, the telephone rang, and it was the sergeant saying, "Duck," which meant take cover. And all I said was, "I cannot, I've got too much information coming through." And he just said, "I'll leave it to you." The most uncanny noises, these aircraft, and they started diving. And the Stuka shrieks, and it makes the most blood-curdling sound. And then there's the shriek of the bomb, of course, as it drops. Carried on, I don't know quite how long it was at all, until the line went dead.
For her gallantry in staying at her radar post throughout the bombing, Avis Parsons was awarded one of Britain's highest honours, the Military Medal.
I received it from the King at Buckingham Palace, and he decorated 306 people that morning, only 3 women.
Of all the radar stations bombed, just one was temporarily put out of action. Goering was so convinced that Britain did not have radar that he never ordered his bombers to attack the radar masts again. It was to be his greatest blunder, and would have enormous consequences for the battle for Britain. Britain had her back to the wall as wave after wave of German bombers launched a barrage of terrifying attacks. As each flight came across the English Channel, they were plotted by the WAFs of the Royal Air Force.
You would be getting more and more coming in. And you'd know, you'd look across to somebody else and they were getting a lot in, and you'd wink, you know, or something. You knew that was something big coming in.
You just got on with the job. You just did the job. It was there. You did it. There's no anxiety at all. If you're going to be bombed, well, you were going to be bombed.
Sometimes, as they plotted the Luftwaffe, these women knew that the bombers were headed for their hometowns.
You thought of houses and roads and people. And if your house had been very badly damaged in bombing, you knew what was coming to somebody. All you could do was pray.
As the battle increased, the hard-pressed Germans were unable to understand where the RAF got their apparently inexhaustible supply of fighters. The reality was that the RAF was fast running out of reserves. Had the Luftwaffe continued to bomb the RAF airfields for just a few more days, the British might have lost the battle. But radar made them appear so much stronger than they actually were. By the end of September 1940, the battle for Britain was over. Goering's mighty Luftwaffe had failed to win mastery of the skies over Britain. He had lost over 1,200 aircraft, and the Luftwaffe would never bomb Britain by daylight again.
I think that one intelligence failure of the Graf Zeppelin mission cost Goering the Battle of Britain. That's my opinion. And had we lost the Battle of Britain, what would have been the consequences?
Radar had helped to save Britain. But it was just one victory in the battle to defeat Nazi Germany. If radar was to win the war, then Britain needed help. That would come from the colossal technological expertise of America and would push radar to its very limits. In the battle for the Pacific, by summer 1940, as Britain was fighting for its very life, Prime Minister Winston Churchill made a momentous decision. He knew that for Britain to win the war, she needed America's engineering and manufacturing resources.
An important aspect of the war was that while we had the creative ability to develop the most advanced radars in the world, we did not have the production capacity, and we needed the Americans' productivity resources.
In August of that year, Churchill authorized Henry Tizard to form a team and unconditionally to share the secrets of radar with the United States.
The British heads of military branches were very reluctant to share some of these early secrets with the Americans. Churchill had a different attitude. It was, we can't do this by ourselves. We don't have time to worry about secrets.
Amongst the papers and plans of this highly secret mission was something that would forever change the course of the war, the cavity magnetron. Invented by two British scientists, this device greatly magnified the radar's signal and could track objects that early radar could never do.
This was a device that looked a lot like a clay pigeon used in skeet shooting. It could fit in the palm of a hand, yet it could put out on a wavelength of 10 centimeters microwave energy, powerful radio waves that were about 1,000 times more powerful than any other transmitter known on that wavelength. So this was this wasn't just an evolution, this was a revolution.
Ironically, this quantum leap in science was not sent to America under armed guard. Although shrouded in secrecy, it made its momentous journey via London taxicab, passenger train, and ocean liner. But when the cavity magnetron finally arrived in America, it stunned its top scientists. This would open the doors to the US radar program, and in doing so, would also help modernize their own armaments.
When the British opened up this black box, and especially showed the magnetron, it blew the Americans away. They felt that overnight, their own fledgling microwave radar techniques had been advanced 2 years. The official historian, James Finney Baxter, in describing the magnetron, wrote that when the British brought one to America, they brought the most valuable cargo ever carried to our shores.
Research immediately started at MIT, the Massachusetts Institute of Technology, in a laboratory called the Radiation Laboratory, or RADLab. RADLab enlisted the best and brightest minds that America could offer.
There began a recruiting drive, the likes of which we never saw again. They brought in the best-known physicists in America. They would routinely get a call that would say something like, "Come join this effort that we have."
I was recruited by telephone at the end of 1940 with an encouragement that suggested that maybe the draft board would look favorably upon me if I were working in a technical field.
Such was the secrecy surrounding RADLab. The American public were oblivious to what was being developed. Most were completely unaware that the clock was ticking its countdown to war. But for the newly recruited scientists at MIT, the importance of their work was not lost on them.
This was an important project. There wasn't any question about that at all. We were going to get this solved, and everybody was expected to pitch in and do it, and we were anxious to get this job done and maybe even get back to our regular jobs before too long.
As 1941 wore on, few top American officials now doubted that the US would soon be fighting Hitler in Europe. But initially, the sword of war was to strike from a different part of the world completely. On the morning of December the 7th, 1941, aircraft launched by a carrier task force of the Japanese Imperial Navy struck the Navy base at Pearl Harbor in Hawaii. In the 110 minutes of the attack, American forces suffered over 2,400 killed, 300 planes lost, and every battleship in the Pacific Fleet was either sunk or damaged. A shocked America charged into war with Japan. The question on everyone's minds was, how could the Japanese have made such an attack undetected? What very few people knew was that the Japanese had been picked up on radar. The US Army had deployed 5 new mobile radar stations on the island of Oahu. These were long-range sets, capable of detecting intruders as far away as 150 miles.
This radar was being operated by 2 Army personnel. They were actually there in training, and they were due to shut down at 7 a.m. And the junior officer persuaded his boss to keep it open a little longer. And lo and behold, there was the blip of what turned out to be the Japanese air invasion. They actually tracked the planes for a while. They relayed the information to their command post. And the lieutenant on duty failed to put the pieces together. He had heard this vague rumor of some American bombers doing from the mainland around that time, and he thought this must be what they were seeing. He told them to forget about it. They tracked the invasion into about 20 miles when the planes disappeared behind some hills. The rest, as they say, is history.
But the radar fiasco at Pearl Harbor had a valuable silver lining, since it did much to alert the US military to the importance of radar and to speed up its development and deployment.
The arrival of Pearl Harbor clearly presented a different atmosphere in which to work. The principal change that I can detect in looking back is that the military were now definitely interested in what was going on in our experimental laboratory.
Thrust into the crucible of a bitter Pacific War, and with nearly all of its surface fleet decimated, the US High Command had only one choice left open to them as to how to take the war against the Japanese. It had to be the submarine service. But could the new radar sets, with their most advanced capabilities to date, be outfitted for submarines in time to avenge the attack on Pearl Harbor? The attack on Pearl Harbor had severely damaged the US Pacific Fleet. A shocked America, repulsed by the unprovoked aggression of the Japanese, launched themselves into war. Hours after the attack, on the afternoon of December the 7th, 1941, the chief of US naval operations issued an order to execute unrestricted air and submarine warfare against Japan. With this call to arms, the submarine force went on the offensive. Hundreds of new recruits volunteered to join the silent service. They were to be the pioneers of the new technology of submarine radar.
The training was very hard, actually. There was a 50% failure rate at submarine school. It was very strict.
I knew nothing about radar when I first went on a submarine. I didn't even know what the word was. And for some time, even the word was classified. But I began to learn about it because I had to.
Alongside these volunteers, dozens of the silent killers were being built and rushed into service. Nothing was going to stand in their way. In May 1942, a unit was formed that combined the scientists of MIT and the armed forces. Its purpose was to streamline any bureaucratic obstacles that might hinder the development of radar. Now, science could work hand in hand with the military.
They had all kinds of spec lists for anti-aircraft guns, for ships, for search and warning, for airborne interception, for bombing, all kinds of different uses. And they would come and tell about their needs. And at the same time, the Rad Lab would say, we have this new thing that could do something you never thought of before, maybe. What do you think about that? So you had this unique give and take. Shopping list, but also this kind of like kid in a candy store thing, like, oh, I want that, you know.
I have to say the word red tape, I don't think had ever been invented back then. None of us had ever heard of the idea of having our work interrupted by people who were keeping track of things on pieces of paper to see how much they cost or whether they were in stock or anything of that sort.
Now, the U.S. submarine service was ready to come into its own. Utilizing the new technologies pioneered at MIT, radar was being developed that would prove more than equal to the Japanese.
Japan entered World War II with its own radar systems that were maybe 6 months behind the American and British systems. By the end of the war, the best assessments from the intelligence debriefers showed that they were about 4 years behind.
Using the newly developed radar units, U.S. submarines could now pinpoint Japanese vessels and aircraft from much farther away, well beyond the upper limits of the inferior Japanese electronic equipment. The tide of the Pacific War was about to be turned, so much so that a Japanese officer likened the battle between the Americans with their new radar technology as being like a fight between the sighted and the blind. The operators of these new eyes of the submarine were held in awe by their fellow crew members.
The first radar man we had, we looked at him as God. Radar was a very important item for submarines during World War II, and I think it gave us the edge over the enemy because we could see what was going on and he couldn't see us while we were watching.
The ability to see and not be detected was honed to a fine art. But it was not just down to the radar operators to stand watch. It was a team effort.
When we were on the surface, we'd have a watch section. There were 3 watches. There'd be a radar operator. He'd have a relief. There'd be the lookouts. There'd be the radioman. It was a whole watch section. 1/3 of the crew was actually running the boat.
It's hot, cramped, so you're sitting on this black conning tower with a red light, eerie kind of thing you might say. It was dark. But also, your screen showed up better in the dark.
Then the initial radar also was manually trained, the antenna was. So the operator stood and he cranked the antenna manually. And that was tiresome. You had to peer into that scope constantly. That caused eye fatigue. And if the operator was training the antenna and just happened to look away for a second, he could miss seeing a target.
With the new radar, the submarines were continuously locking in and destroying the enemy.
When you get a contact, of course the adrenaline kicks in.
Dive! Dive!
Everybody's coming down, manning their stations forward, the bow planes, the stern planes, the helmsman. We go to the sonar gear, and we're on our way down.
Using their radar, the submarines were able to operate in hunter-killer groups and take control of the Pacific.
Another use that we had for the SJ radar was to home on other submarines, especially when our submarines were operating in a wolf pack, and we sort of lost track of where they were. We could seek them out quite well by homing on their own radar emission.
Using these tactics, the radar-equipped submarines were able to hunt down Japanese shipping, slowly squeezing the life out of the empire's industrial and military might. But it was not a one-sided fight. Whenever the US submarines torpedoed a ship, the Japanese escort ships would ruthlessly hunt them down. Once below the surface, radar could not protect them from the ensuing depth charges.
Well, it feels like you're sitting in a drum and somebody's hitting it with a sledgehammer, depending on how close. If it's not too close, you hear the detonator go off first. It's 2 click, 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 bang. And if it's close, you don't hear the click, click, you just hear the bang. The boat will rock a little bit, depending on how close the depth charges come.
Everybody has their own level of fear. Some guys can take it a little more than the other person, but everybody is afraid of them.
We had one young fella get on his knees when we was being depth charged. He was scared. He was scared. He thought that we were going to rip open and this was his day, that he was going to die. Yeah.
By mid-1944, the Japanese were still unbeaten. But it was becoming evident that they were beginning to lose the war at sea. More and more radar systems were being rushed into the conflict. But there was one system that would play a vital but little-known role in delivering the bombs that would end the war. By late 1944, the Silent Service had the finest radar that science could provide. Refining their methods of attack, the American submarines became the single greatest enemy of any ship flying the Japanese flag. Shortly after midnight, on the 21st of November 1944, the USS Sea Lion was patrolling on the surface off the coast of Taiwan when she picked up a radar contact.
Radar picked up an object which we thought was land because it was at a great distance, about 40,000 yards, until the radar operator said if it's land, it's moving. So the captain was called to the bridge, and he decided to go where the radar picked up the pips. And as we get closer, we could see that there was 7 ships in the formation, which was a task force. 2 of the ships were very, very large. Now, we could not see the ship. This was radar that was telling us what was there. They were going straight on no zigzagging.
Stand by. Fire 1!
We got 3 hits on the first target, and we spun around and fired 3 torpedoes from the stern tubes at the second battleship in formation, and we got 1 hit. When we hit the ship, sure, there was a lot of jubilation.
With its radar, the Sea Lion had sunk the 31,000-ton battleship Congo. It was the only battleship to be sunk by a solo submarine in the Pacific. Her loss struck another severe blow to the Japanese Navy.
The devastation that the American submarine fleet wreaked on the Japanese with these microwave radar systems, I think eclipsed the devastation done by the U-boats in the Atlantic. It was immense and not much talked about in subsequent histories.
As the war elsewhere in the Pacific escalated, so too did the use of radar. U.S. Naval Service vessels were now fully equipped with every technological weapon that the scientists from MIT had developed. In a radical move, instead of commanding the battle from the bridge, ships' executive officers now fought the enemy from the Combat Information Center. Here was a whole battery of communications, navigation, plotting, and radar. Once in range of the all-seeing eye, no Japanese ship was safe. From the seeking out and plotting to the radar-controlled guns, the enemy was virtually doomed from the first blip on the screen. Fleet carriers bristled with radar. They had early warning, surface search, fighter control, and height control, all with one purpose: destroy the enemy. It all came to a head in June 1944. In the battle for the Marianas, with the aid of American shipboard radar, more Japanese aircraft were destroyed than the German Luftwaffe lost in the whole of the Battle of Britain. One Japanese admiral identified the single greatest U.S. strength as its ability to control its fighters by radar. The gateway to Japan was beginning to open. But before America could hurl its might at the Japanese mainland, the islands of the Pacific had to be taken. But what was to follow was to be one of the bloodiest campaigns in the entire war. Each island was proving harder and harder to take, as the Japanese defenders fought to the death rather than surrender. In early 1945, after a 36-day assault on Iwo Jima, the US counted over 19,000 injured and 6,800 dead. The toll on American lives was becoming too much to allow. In the US plan for the invasion of mainland Japan, the official estimate was that over 500,000 American lives would be lost. This was too high a price to pay. Again, radar would come to the aid of the Americans.
Once the Americans pushed up to the Marianas Islands within about 1,500 miles of Japan or so, they were close enough to launch airstrikes with radar-guided bombers on the Japanese home islands.
American B-29s were now able to bomb the Japanese mainland. Using the latest RadLab airborne search technology, they laid a devastating trail of destruction. By mid-June 1945, US bombers had reduced many of the principal Japanese cities to rubble. The skies belonged to America, but still Japan would not surrender. The decision was made to use the ultimate weapon to end the war. Shortly before 3 o'clock on the morning of the 6th of August, a B-29 took off from the island of Tinian, southeast of Japan. The aircraft was using a radar navigational system called Eagle. Within the B-29's bomb bay lay a 10.5 feet long atomic bomb called Little Boy. As the plane neared its target, the bomb was made ready. Around its girth were 4 radar fuses. At 8:15 a.m., the bomb was released over Hiroshima. Each fuse constantly bounced signals off the ground, and at 1,900 feet, the radar fuses ignited the most powerful weapon known to man. Three days later, a second nuclear weapon, again assisted by radar, exploded over Nagasaki. World War II was over. The explosive fury of the atomic bombs that ended the war also heralded the end of RadLab. At MIT, over 150 radar models had been designed and developed. American industry had played its part by building nearly 1 million radar sets.
Hiroshima was a conclusion, but the radar systems that were produced during the war period played a very key role in almost every single battle.
The atomic bomb only ended the war. Radar won it. There was no other technology that was more important to more aspects of war, and it was the unique integration into all aspects of warfare that made this the most powerful and pervasive weapon of World War II.
From a leafy lane in England to helping deliver the most powerful weapon in the world, radar had come a long way. But in 10 short years, it had changed the face of war forever.
I took an engineering degree at the University of London, and in 1934 joined the development laboratories of standard telephones and cables, where I was working on development of new systems of telecommunications. I also happened to work on a device for the Army sound locator system that was being built on Romney Marsh. At that time, 1935, it was our only method of detecting incoming aircraft. Could achieve a range on a good day of about 5 miles. And I designed a piece of equipment for that system. Then in 1938, I was headhunted by the Air Minister Research Establishment. They wanted a communications engineer because of the problem of passing all the radar information into Fighter Command. It was quite a communications problem. Someone recommended me, and I joined them on I think it was the 3rd of September, 1938, in the middle of the Czechoslovakian crisis. I was summoned by telegram to report to Bawdsey. This was on the 1st of September, I think. I arrived there. I met Rowe, who was then running the research station. I signed the Official Secrets Act, and with a colleague of pre-Bawdsey days who had worked with me at Standard Telephones, we set off late in the evening to go to Fighter Command to put the first radar filter room into Fighter Command. We arrived at Fighter Command the next morning early, met the Chief Signals Officer, Wing Commander Rodney, were led in to meet the Commander-in-Chief, and we told him what we wanted to do, and he allocated us a very dusty cellar in the basement of Bentley Priory. And within 3 days we had built, we had post office engineers and a gang of carpenters and other helpful people. We had created the first radar filter table onto which all the plots from the CH stations were placed before being transmitted upstairs to the operations room where the Commander-in-Chief presided. We, at Bawdsey, we were sitting there lunching together, we said, well, the Germans must know what we're doing. We're building these 360-foot steel towers for the transmitter, 240-foot wooden towers for the receiver. Standing out on the skyline, they could not help but see them. And they must therefore realize this is a radar system, and they must be investigating it. They probably know a lot about it. We had a high degree of secrecy, but you could never be sure. Now, one day, it was the 3rd of August, 1939, the CH station just north of Southend called Canewdon observed a massive echo approaching from the east at about 60 knots. Far bigger echo than they'd ever seen before. And their first reaction was that it was an invasion fleet with barrage balloons to protect it from an air attack. But they soon realized that was not so. It came within about 30 miles of the coast when it turned north and flew the whole way up the east coast. We tracked it on radar the whole way. When it was approaching Scotland, Fighter Command set up 2 aircraft from RAF Dice, not to shoot it down because the war hadn't broken out, but to have a look at it. And they secured a photograph. It was the Graf Zeppelin LZ-130. It flew to Scotland, where it turned eastwards and back across the North Sea. The whole operation lasted most of the day. Now, we concluded that they had been accurately observing our radar system, measuring the frequencies, plotting the position of the stations, and all other technical information. So they would have gone back loaded with that information. And therefore, what would their reaction be? We assumed that as soon as war broke out, and we knew war was coming, they would probably bomb the stations, particularly Bawdsey. But we could expect a massive attack on the radar system. For that reason, Bawdsey was evacuated as soon as 1st of September, as soon as Germany invaded Poland. And we put in hand measures to deal with the possible bombing of stations, such as mobile reserves. That did not occur. No, there was no attack launched at the beginning of the war, June, July of 1940, no attack. No attack came until the 12th of August, 1940, when the Luftwaffe attacked, first of all, the CH station at Dover, then one just north of Canterbury called Dunkirk, then Pevensey, Rye, and they did significant damage to all of them. There were one or two casualties. Most of the, well, all the stations were off the air for that day. In the afternoon, they attacked Ventnor in the Isle of Wight and did a great deal of damage. In fact, it was out of action for, I think, 4 weeks after that. Now, our conclusion at 6 Group, where I was serving on the staff at that time, was that they'll come back tomorrow and finish the job. And if they don't come back tomorrow, they'll certainly come back the day after tomorrow and finish the job. But they didn't come back. And we could never understand that. They did one more attack on the 18th of August on the CH station at Poling, and that was the only other significant attack on the radar system. Had they persisted as efficiently as they did at Ventnor, and Fighter Command would have had no radar cover for weeks on end. There would have been a complete gap through which Goering could have poured his bomber forces and destroyed all our fighter airfields and laid the way open for the invasion fleet which Hitler was holding in reserve to launch once Fighter Command had been destroyed. That remained a puzzle throughout the war. It was only after the war, some years after the war, when I happened to meet General Martini, who was the chief signals officer of the Luftwaffe throughout the war, a very able officer. And I said to him, General, why didn't you destroy our radar system at the outbreak of war? He said, you didn't have a radar system. I said, well, how was it we tracked the Graf Zeppelin from the Thames to Scotland? I've never seen a man so shaken in a long time. He said, you tracked it? I said, and then I described it. He then told me that her Dr. Bruning was on board with about 20 scientists with all the receiving equipment in the world. They came back and reported they could detect no radar transmissions. They could detect noise which they thought was from the British grid system sparking over. Now, had they got that right, and we now know the reasons, I won't go into that now, but had they got that exercise right, had they detected that we had a radar system, Martini, who knew the threat that radar posed to the attacking forces, would almost certainly have been able to persuade Goering to really destroy the radar system. As it was, Goering was entirely dismissive of what he called these radio installations. You don't fight a war with radio installations, you fight them with bombers. He might have persuaded Goering to take a different line.
One of the war's most carefully guarded secrets has been revealed. This is radar, an electronic eye penetrating darkness, cloud, and thickest fog to aim our guns and bombs, to bring our aircraft safely home, to warn against attack, against storms, against navigation hazards. With urgent war demands accelerating 20 years' research in electronics, radar's potential forced swift advance in Air Force operational techniques, multiplied our striking power, and held the enemy off until he could no longer strike back. This is how radar works. A transmitter sends out a constant stream of ultra-shortwave impulses, which probe the sky like giant searchlight beams at a speed of 186,000 miles per second. This oscilloscope registers the impulses and indicates the position of the transmitter by this large peak. When the radar beam strikes a solid object, such as a plane, it echoes back and appears on the oscilloscope screen as a smaller peak. By measuring the elapsed time and by focusing the radar beam like a giant searchlight, the plane's direction and distance are easily calculated. To carry out a war strategy rooted in the laboratories and the factories, an amazing variety of highly specialized radars has been developed. This is the early warning system, first guard against enemy attack. The radar that cost the Luftwaffe the Battle of Britain. Blanketing the sky in every direction, the early warning system is designed to detect an approaching bogey 100 miles away, to determine its azimuth and speed, to alert searchlights, gun crews, and night fighters. As the bogey draws nearer, this radar system, designed to throw a more sharply focused beam, takes over. Its job, to secure altitude and range data. This information is immediately forwarded to the plotting center. Here, location, course, speed, and altitude of the approaching aircraft are computed long before it comes within striking distance of the target installation. Continuous tracking from the moment a bogey is spotted provides a steady flow of firing data to gun crews and searchlight batteries who remain in constant communication with radar headquarters. As the plane enters gun range, anti-aircraft crews switch on their electronically guided searchlights. Radar is so sensitive, so precise, that once a searchlight beam focuses on an aircraft, escape becomes almost impossible. With AA guns automatically aimed by fire control radar, visibility is no longer of prime importance, but searchlights are triangulated on target to double-check range calculations. Final reports funnel into the plotting center, and the action signal goes out to the guns, already waiting to shoot down the intruder. To make certain that Allied guns would not mistakenly shoot our own planes from war-crowded skies, the Air Forces turned to another radar device, the IFF, named for its ability to identify friend or foe. This device automatically establishes identification by an exchange of signals between ground radar and the aircraft in flight. When an unidentified plane is detected, an interrogator responder sends out a questioning signal. A transmitting device carried aboard all friendly aircraft is automatically set off by this signal and responds with an extremely powerful energy wave which causes a deviation in the normal oscilloscope patterns. If the plane is unfriendly, the normal echo pattern remains unchanged. Quick to exploit its ability to identify the enemy at all times, the AAF evolved new radar-based combat techniques designed special aircraft for night fighting. This air defense method is called GCI, for ground control interception, and employs the same type of radar as that used to monitor D-Day air traffic over France. The dial records relative positions of friend and enemy, makes it a simple matter to vector our planes in for the kill. Unlimited in its application, radar has saved the lives of countless airmen. Throwing this emergency switch prior to ditching a battle-damaged bomber causes a continued wide impulse to be transmitted, enabling ground stations to locate the falling plane by triangulation. The device is destroyed automatically, but before the bomber hits the water, an air-sea rescue plane is on its way to the ditching site. Maintenance of air transport schedules, vital in far-flung military operations, depends heavily on radar. Uninterrupted delivery of urgently needed materiel often forces disregard of weather hazards. When pilots low on fuel find runways closed in by fog, or when quick shifting weather blots out a tiny Pacific landfall, endangered planes are helped to safety by a ground control approach radar system known as GCA. No part of this system is carried aboard the plane, but the pilot receives direct verbal guidance from the ground-based radar man. These dials show the transport's position relative to the runway. The operator's first task is to direct the pilot into correct position for a landing approach. As the transport nears the runway, it is picked up and registered on the GCA's oscilloscope. The GCA antenna has only one range and one azimuth, and if the approaching plane is correctly vectored, it will appear as a luminous patch moving between parallel lines. The operator notifies the pilot when the plane is over the glide path, and the transport settles down, literally talked onto the runway for a safe and easy blind landing. Despite its military usefulness, radar's peacetime possibilities have yet to be fully explored. But at war's end, giant cargo planes operating halfway across the world point to an indisputable fact. In peace, as well as war, the development of radar is now inseparable from the development of aviation.